Good morning. This is Meghna.
And Umang.
This is a small presentation on our project Fast Controllable Induction Heater and Display. Our motivation for the project was that induction heaters have become a widely used technology in various fields, including medicines, food industry, basic mainly. So there is a need for flexible and affordable induction heaters, which are not very expensive and they do not have limited temperature controls. So also because of the various advantages induction heaters have over conventional heating methods, we wanted to design a affordable induction heater.
So our basic principle for the circuit was basically an induction heater is a type of electrical device that uses principles of electromagnetic induction and the concepts of eddy current. Basically, it consists of an AC power supply, an induction coil, and a workpiece that is placed within the coil. AC power is supplied to the coil, creates a rapidly changing magnetic field. If a conducting material, example a ferromagnetic material, is present, the magnetic field induces eddy currents, and these eddy currents are responsible for the heat generated in the coil. So, after reading couple of research papers, we have found this research paper to be interesting, and this used the implementation of LLC resonant load matching. So, LLC resonant load matching is based on tuning and inductive and capacitive components of a resonant circuit to a specific frequency and then matching the load impedance by adjusting the duty cycle of the input voltage. This technique offers high efficiency, precise power transfer, and reduced electromagnetic interference, and is commonly used in power supply, battery chargers, and motors. And after referring to couple more circuits which uses ZVS and Royer oscillators concept, we found them to be more easily implementable in our lab. The following two are the ZVS and Royer oscillators. ZVS is zero voltage switching, a type of resonant circuit uses a half bridge or full bridge inverter with resonant components to achieve zero voltage switching of the power switches. This means that the power switches, typically the IGBTs or MOSFETs, are turned on and off when the voltage across them is zero, minimizing the switching losses and improving efficiency. Whereas the Royer oscillator is a type of self-oscillating circuit, uses a transformer and two transistors to generate a high frequency AC for induction heating. The transistor alternately switches on and off, creating a resonant circuit with the transformer. So the ZVS circuits are mainly known for their high efficiency, high power density, and good load adaptability. Hence, after seeing these advantages, we have chosen to build our induction heater based on the ZVS circuit.
A ZVS circuit works similar to an A-stable multivibrator, where it works based on the switching of two transistors. So initially, if we give power supply to this circuit, then both the transistors will be switched off, but slight difference between the transistors may lead to one transistor turning on before the other one. Say M1 switches on before M2, and as as M1 turns on first, its drain voltage drops rapidly, and capacitors act as short circuits to rapid changes in voltages. So C1 will act as a short circuit, and as the node Q dash, the voltage near node Q dash drops, the gate voltage of M2 will also drop, keeping it switched off. With M2 off, the voltage across node 2 and the gate node 2 and the gate of M1 will be high, keeping M1 on. Now the capacitor C1 will be charging through the resistor divider, so the gate voltage of M2 rises and eventually increases above the threshold voltage, thereby turning M2 on, and its drain voltage drops rapidly, turning M1 off. Through the resistor divider, the capacitor C2 gets charged, raising the gate voltage of M1. This will eventually turn M1 on and M2 off, and the cycle continues. So ZVS works like an A-stable multivibrator with inductors and capacitors. The circuit oscillates at the resonant frequency given by F is equal to 1 by 2 pi under root LC. So over here in the circuit, when Q1 is high, it implies that the gate voltage of Q1 is high. That is, the LC circuit voltage swings up to down. On the way down, it pulls the gate voltage of Q1 down and turns it off. The drain voltage of Q1 increases and raises the gate voltage of Q2, turning it off. The LC circuit voltage swings up to down again and then pulls the gate voltage of Q2 down. This cycle continues and the switching continues.
You're done.
The switching results in alternating current in the LC, creating LC oscillations, which is required for heating purposes.
So these are a few simulations which we performed in multisim. So as we can see from the plot, the reason the reason for the flat line is as follows: when the drain of the transistor switches and the drain voltage changes rapidly, the fast change through CGD creates a negative feedback to the gate and won't allow the gate voltage to change easily as long as the drain voltage is switching, hence creating a flat voltage area around the threshold voltage when the transistor is switching and the drain voltage is changing fast. So as we can see from the plot, this is the drain voltage across Q1, which is a sine wave with a flat. And if we try to plot the drain voltage of Q2, it will be simply the inverted version of this thing, which implies we get the total sine wave, one part of it in Q1 and another part in Q2. Moving forward, when we see the current in the inductor, we can see its peak to peak voltage, peak to peak current is around 60 amp, which is far more sufficient to heat up to 10 degrees Celsius. This is the Monte Carlo analysis for our circuit.
This is the design for the controller circuit, which will be in series with the heating circuit. So the comparator circuit uses LM358, which is a comparator, and it compares the two input voltages and according to that gives a high or a low. So we use a thermistor, which is a temperature sensor, and its resistance changes with the change in temperature around it. So the potentiometer is used in such a way that we get a required temperature, and based on the voltage division between the thermistor and R1, we get a high or low as an output from the comparator. For example, if the temperature of our inductor coil is less than the required temperature, then we get a high output and the relay switch will be switched on. So the circuit will be complete and current will be flowing into the heating circuit. But if the temperature crosses the required temperature, then we'll get it low and the switch will open, thereby stopping the current flow. And the switch will be closed only when the temperature of the inductor again goes below the required temperature. So in this way, we're ensuring that the temperature is maintained. So this is the circuit of only the controller circuit. When we are integrating it with the heating circuit, we thought instead of the thermistor, we'll use an temperature sensor and give it as feedback, give it as input to the negative terminal of the LM358.
So moving forward to the hardware implementation of our circuit. So our main design of induction heater with ZVS circuit had few high voltage capacitors and inductors used were air core inductors. As its components were not present in the lab, we had to make use of the non-working inductor heater provided by Sir. Hence, we removed the high voltage capacitors and air core inductors and connected to our circuit. And the main inductor, which is parallel to the high voltage capacitor, was basically replaced by the induction coil present in the induction heater. So we gave the power through the power supply of 12 volt, and then we have measured the current using the multimeter and measured the voltage and checked the plots using the DSO. After this, we connected our circuit to the controller circuit to control the circuit. The problem we faced in the problem we faced in this was the induction was a vessel was not getting heated up to the certain mark which we decided it to. Hence, we had to either remove the circuit or or we had a choice of using a transformer which could help us to step down the voltage from 220 volt from the supply power to around 50 volt, so that we can heat our induction vessel to certain temperature. But there was a main problem that we were not using a ceramic plate, and the circuit was completely open, which could be dangerous, and the current could go very high. So in this implementation, our main focus was to find a flaw in the induction heater, which was provided by the SIR. So hence we started working on various problems which could cause this induction heater not to work. Firstly, we used the tool multimeter to check the potential of various points and also check if the soldering was not dried out. After doing this, we found out that there was a problem with IGBT, insulated gate bipolar transistor, and hence we tried to remove it and try to check it if it was working individually. After doing so, we came to a conclusion that IGBT transistor was working fine, but there was a problem in the soldering. And after fixing, we tried checking for more problems and apparently found that there was a problem in a high voltage capacitor, which was not also soldered properly. After finding these issues and trying to fix them, we checked our final circuit using multimeter and trying to see the DSO plots. And after fixing these and soldering it again, we have tried to connect it to the main power supply and found and fixed the circuit. So after repairing the induction heater, now our final challenge was to make a user interface which could help us to increase or decrease and to display the temperature.
This is a block diagram of our final circuit where we have a conducting material, a coil, a controller, user interface, and a power supply. So power is supplied to the circuit, and the user gives an input, which is given to the controller, and from the controller the coil is connected, where coil is supplied with high frequency AC. Now the coil generates eddy currents and results in heat in the conducting material. The controller also gives the user interface the temperature to be displayed. These are the images of our final hardware circuit, where we have the induction coil, the controller circuit, and the user interface. This is the working of our induction heater. We supply power to the main board through the phase and the neutral lines. The phase is connected directly to the fuse, and the fuse is connected to the interface capacitor. Here we get an AC input, and this is an input to the bridge rectifier, the AC terminals of the bridge rectifier, which outputs a DC voltage. And this voltage is divided between two parts of the circuit, the circuit that provides the auxiliary power supply, and also the circuit to give power to the IGBT. Now, the positive and the negative terminals are connected, are as given as a power to the auxiliary power supply, which is responsible to provide us 18 volts or 5 volts or 3.3 volts required to control the microcontroller unit of the circuit. Now, the auxiliary power supply has a transformer which outputs 18 volts, and this is connected to a voltage controller which results in 5 volts that is required for by the MCU. The MCU's main purpose is to act as a IGBT gate driver. It also is responsible to give power to the display, the user interface. It controls the buzzer and the fan. Also, one of the main functions is that it takes the signal from the temperature sensor, and that is displayed for the users to see. Now, the IGBT circuit is connected to a tank capacitor which operates at high voltage and high frequency, that is in parallel with the main coil. So, the switching of the current in the coil is based on the control from the MCU. It switches at high frequency, resulting in eddy currents in the conducting material. The main challenges that we faced was the induction stove that was given to us wasn't functioning, so it was challenging to decide which parts were working and which weren't. Also, making the display circuit was very challenging. because specifically we face several difficulties in finding TM1628 IC, which is an LED controller that operates on a 1 by 7 to 1 by 8 duty factor. So improvements where we identified the root cause, damaged MOSFET and dried solder. We fixed it, and we got our circuit to work. In conclusion, the design and implementation of a fast controllable induction heater with display has been successfully achieved in this project.